Yeah, in the last class, we seen about the data types. No, there are two primary data types are there. One is net data type and variable data type. Net data type represents the physical wires in the design. So basically, in the net data types, we have wire, var, band, triar, tri register, supply 0, supply 1. Those are the net data types. Okay. So these are the net data types. Okay. And next, so these are the netted data types, and you have variable data type. Variable data type means we can store the last assigned value until it changes. Okay. So this is declared by using a keyword called reg. Okay. The default value for netted data type is z. Default value is z. Okay. So z is nothing but like it will be like high impedance state. Okay. It will be look like so. This is like no clear. Okay.
Is it clear now? Your response. Is it clear? Is it clear? Hello. Is it clear? My voice is clear. One second, one second. Yeah, is it clear? Hello. Is it clear? Waiting for your response. Is it clear? My voice is clear. Anyone give response?
Yes, sir.
No, it's clear, no? Okay, okay, okay. Yeah. So, so the default value for so mainly this reg data type we are using in the procedural blocks. Okay, so this mainly used in procedural block. The default value is x. The default value is what? X. Okay, some more data types are there. So this net data type and this wide these two net data type and variable data types are unsigned data types. Unsigned data type means when you are giving some means negative value, it will display in terms of 2's complement, but the value will be positive only. Okay, these are unsigned data types. Okay, and what are signed data types means there is one more data type, that is integer data type. Okay, so what is the default default size? So that means if I am considering reg a, so default size is how many bit means 1 bit only. Okay, so if I am considering wire a, what is the default size? So this is 1 bit only. Okay, default size is 1 bit only. Okay, and next integer data type. So what is integer data type? Integer data type means integer I if I consider. So in order to store some negative numbers. Okay, integer data type. So integer data type means so you want to store some negative numbers, we are using integer data type. Okay, so this is signed, we can call as signed data type. Okay, this is called as signed data type. Signed data type. Okay, and my voice is clear now? Anyone give response so that I will move forward?
Yes, sir. Clear.
Okay, okay, sure, thank you. Okay, so here suppose what is the width of this one is width is 32 bit, width is 32 bit, and the default value is x. Default value is x, and so size is 32 bit. Okay, this is a signed data type. If you want to store some negative values, you need to use integer data type. Okay, and next you have real data type or float data type. Float data type means in order to store some decimal numbers. Okay, so in order to store some fractional numbers, you are using float data type, fractional numbers. Okay, so fractional numbers you are using the float data type. Okay, so this is also unsigned, this is signed data type. Okay, so this is a signed data type, signed data type. And what is size of this float data type is 64 bit. For size of this float data type 64 bit, and this is a signed data type. Okay, and default value is also x, default value. So what is the default value? Default value is x. Okay, so this is signed data type. And one more data type is nothing but time data type. Time data type is mainly used to display the simulation type. Okay, display the simulation type. Okay, so this is time data type. Okay, and so that means I told you the synthesis. No, synthesis is nothing but I told you in the last class. What is synthesis? What is synthesis? You are converting your code into hardware or gate level netlist is nothing but synthesis. No, so there are synthesizable constructs and non-synthesizable constructs. Okay, so what are synthesized means in this data types? What are synthesizable data types? Synthesizable. So synthesizable data types. So synthesizable data types are you have wire data type. Okay, and WAN data type. These we can convert into hardware. Okay, var data type, and next reg data type. Okay, and next vectors. Okay, vectors I will tell you. Okay, it will come vectors and arrays. Okay, vectors and arrays, these are synthesizable data types. Okay, what are non-synthesizable means those will be not converted into hardware. Okay, non-synthesizable data types. Non-synthesizable data types are you have float data type and you have time data type. Time data type. Okay, so this is about the data type. Did you understood what is data types? How many data types are there in the Verilog? Shall I move forward?
Yes.
Okay, next you see. So next is gate level or structural modeling. So what is gate and structural modeling means you are using some gate level primitives you are using. Okay, so gate level primitives are nothing but you are using AND, OR, XOR, NAND, NOR, XNOR, buffer and inverter. Okay, these are nothing but gate level primitives. Okay, so what is the syntax means? So you have in the gate level modeling, so you have gate level primitive, whatever the gate level primitive you are using. Okay, gate level primitive followed by the primitive name. Okay, or instance name, what may be the instance name, followed by output comma input 1, input 2, input 2, up to so on, input n. This is the syntax for gate level modeling. Okay, suppose if you see AND gate is there, so AND gate, so this is gate, so gate level primitive AND out followed by in1 in2 up to so on in n, like that. OR is there, OR followed by out in1 into in n, like that. Okay, and similarly XOR. Okay, out followed by in1 into in n. Okay, NAND also out followed by in1 in, so output will come first, out followed by in1 into in n. Okay, NOR also. Okay, XNOR. Buffer is only like suppose if it is a buffer, whatever the input you are giving, you are getting the output. No, so that means I can write buff. What is the input? Y. What is the input? A. What is the output? Y. Input is A, like that. Okay, suppose if it is the inverter, so if it is the inverter, how I am writing? So this is A and Y equal to what? A bar. No, so Y equal to A bar means here I am writing not Y followed by A, Y followed by A. Okay, so this is gate level modeling. Okay, and in the gate level modeling you have one more that is one second, buff if 0 and buff if 1 also there. Okay, so these are nothing but we call as so tri-state buffers. Okay, so that means here suppose this is a buffer and A and output Y, there is one more signal is there, that is Z. Okay, so when Z equal to 0 means you are getting means it will be in functional mode, y equal to a you are getting. When z equal to 1 means it will be in high impedance state. Okay, so for this if I write buff if 0, okay, output comma input like this I can write. Okay, suppose buff if 1 means what, so that means if it is buffer, so this is a and output y equal to a. Okay, so this is one more tri-state buffer. Z equal to 1 means you are getting a. Okay, that is functional mode, and z equal to 0 means so y equal to you are getting in high impedance state. Okay, so for this I can write buff if 1, okay, y comma a, like this I can write. Okay, so these are nothing but gate level, or we can call as structural modeling. Do you understood how I am writing the gate level modeling? Shall I move forward? Waiting for your response.
Yes, sir.
Okay, yeah, okay. Next you see, so this is gate level modeling, and so this is the basic. I think in digital we already discussed the 2x1 mux. So 2x1 mux have how many inputs? So you have two inputs. So you have two inputs. These are the two inputs and one output. And how many selection line? One selection line. Okay. So we already seen the Shannon's equation. What is Shannon's equation? So that means selection bar into A plus selection into B.
B.
Okay. This is the Shannon's equation we already seen. So when selection line equal to 0, which is connected? A is connected. When selection line equal to 1, which is connected? B is connected. Okay, so this one I am writing with the gate level modeling. Okay, so this diagram you implement with the gate means implement with logic gates. Okay, so with the logic gates you need to implement. So here I need to declare, that means here y1, so I need to declare 3 wires, select underscore n and y1 and y2. Okay, so what are the inputs? A, B, select and Y. Okay, so it will start with the module and module name. What is my module name? Mux. And what are the inputs? Y comma A comma B comma selection. These are the port list. Okay, input, output and in-out and bidirectional ports. Okay, and here I am declaring Y is nothing but output, and what are the inputs? Input A comma B comma selection. These are the selection. And these intermediate variables are there, no, that I am initializing with wire data type, wire y1 y2 select underscore n. This is wire. Okay, now this is not, no, this is not. Okay, so this not I am giving the instance as a1. Okay, and next this y1 I am giving the instance as a2, and this I am giving the instance as a3, and this I am giving the gate level instance name as a4. Okay, so not of, okay, I am giving the gate level primitive not of, what is my instance name? A1. Okay, gate level instance name. What is the output? Select underscore n comma select underscore n comma select. Okay, so this I wrote for not gate. Okay, not gate. And next for AND gate, you see AND gate, for this AND gate and what is my instance name? A2 y1 comma a comma select underscore n. Okay, this is for AND. Okay, and next for AND a3 y2 comma b comma select y2 comma b. So y2 is my output. Okay, output followed by input. Okay, in 1 and in 2, like that. Okay, so output is what? Y2 and b comma select. These are the inputs. Okay, this is and next R means what? R A4. What is the output? Y, and what are the inputs? Y1 comma y2 and end module. So this is the 2x1 mux using GLM. GLM is nothing but gate level modeling. Do you
Sir,
understand?
instead of using and 2 times, we cannot use in one.
Why? Because 2 AND gates are there, no? How you can use it one time? I'm
Okay.
representing in terms of gates, no? I'm representing in terms of gates. Based on the Shannon's equation, you will get one AND gate here, and here one more AND gate you need to use.
Okay, sir.
Okay? Yeah? Okay. Is it fine? Shall I move forward?
Yes, sir.
Next, hierarchy of the module. Hierarchy of the module means modules are instantiated inside another module to create a design hierarchy. So design hierarchy means, suppose in the digital we already seen, we implemented the full adder by using what, two half adders and one OR gate. No, okay. Suppose if you want to write the code for full adder, so first you write the code for half adder and you need to instantiate by 2 times and one OR gate is used. Okay. Similarly, if you want to write for the code for ripple carry adder, first you write the code for full adder and you need to instantiate by how many times, means 4 times you need to instantiate. Okay. So that is nothing but instantiation. Okay. So or we can call as RTL integration, we can call as RTL integration, instantiation, or we can call as RTL integration. Okay. So here instantiation of module means module in another high level module. Okay, module in another high level module. Okay, so hierarchical design allows you to organize your design into modules and submodules and creating the structural or modular approach. Okay, so this hierarchy, so where it is helping means, suppose if you want to manage for complex designs, okay, so this can be used for reusability. Okay, we can reuse my design for any number of times. Suppose here RCA is there, RCA you wrote for full adder. Okay, I used this full adder for how many times, 4 times. Okay, so that is nothing but hierarchy. So based on the hierarchy, there are 2 types are there. One is connection by name and next one is connection by position with order list. Okay, this we will discuss what is this connection by name and connection by position with order list. Did you understood the hierarchy, why we are going for hierarchy? Suppose like RCA is there, ripple carry adder, you are writing the code. Okay, for full adder it will take 10 lines of Verilog code, 10 lines of code. Okay, so for full adder you are writing the code, it will take how many lines, 40 lines it will take. Okay, 40 lines it will take. You need to decrease the code complexity. So by using hierarchy, so you are calling the your design for 4 times means it will take around 8 to 10 lines. Which code is optimized? By using hierarchy, the code is optimized. No, writing separately for separate 4 full adders, that is non-optimized code. Okay, so writing this means by using instance, so we can write your code with 8 to 10 lines. Okay, so means you need to write your Verilog code with less number of lines, then it can be optimized. Okay, like that. Did you understood the hierarchy? Shall I move forward?
Okay.
Okay, next you see, so this is so connection by name and connection by position with order list. Here I am writing the basic first full adder by using gate level modeling. This is nothing but basic, I am writing the code for full adder using basic logic gates. Okay, so basic logic gates means sum equal to what, A XOR B XOR C. Okay, and carry equal to what, AB or BC or AC. Okay,
Yes.
okay, so with these expressions I means here I implemented this full adder by using 2 half adders and one OR gate, okay. See here 2 half adders are there, so like one half adder is this one and one more half adder is this one and one OR gate. Okay, so here I need to include the intermediate wires. Wires are nothing but W1, W2, W3. These are nothing but intermediate wires. Okay, so first I am writing the code module full adder. I need to declare the port list A, B, C in, S comma C out, and inputs I need to declare. What are the inputs? A, B, C in, and what are the outputs? S comma C out. These are the outputs. Okay, and intermediate wires I need to declare wire W1, W2, W3. These are the wires. Okay, and for this XOR I need to write XOR. So this is the gate level instance A1. Okay, so gate level instance A1 W1 comma A comma B. W1 comma output. What is the output? W1. Okay, W1 comma input are nothing but A comma B. Okay, and similarly let us take this is instance gate level instance A2 XOR A2. What is the output? S W1 comma C in. S, so S, here S is nothing but output, W1 is one input, it is acting as input, and C in. Okay, that is nothing but XOR operation. Similarly, XOR operation and operation. So let us take W2. This, let us take, this is A4 and this is A3 and this is A2. Okay, so one second, not A2, A5, A5. Okay, so A4, yeah, A4 if you take, so what is the output? This is nothing but AND gate. A4, W2, W2, what are the inputs? W1 comma Cin, these are the inputs. Okay, similarly, and A3, W3, A comma B, W3 A comma B. Okay, and next R A5, C out, W2 comma W3, and end module. So this full adder code I wrote with I designed with two half adders and one OR gate, and this gate, this one I wrote with which modeling? Gate level modeling, GLM, gate level modeling. Did you understood this code? Please respond so that I will move forward.
Yes, sir.
Okay, next. See here. So first here, suppose if I want to write the full adder by using half adder, means first I will write the program for what? Half adder. So module half adder. This is the port load means this is there are two styles are there. So this is style one. Actually, this is style one. Style one means so style 1 means how we are doing. First you are declaring the port list within the bracket. Separately you are declaring the inputs and outputs. Okay, this is style 1. This is style 2. What is the style 2? Style 2 means whatever the inputs and outputs are there, you are declaring within the bracket itself. See here, module half adder. So mostly you follow the style 2 only. So module half adder, input A comma B, output sum comma carry. Okay, I am using GLM only. So this is nothing but G1 and this is G2. Okay, so XR G1 sum comma A comma B. Okay, output followed by input. Okay, and next and G2 carry comma A comma B and end module. Okay, first I wrote the code for what? Half adder. Okay, and in the instantiation, so I am writing, this is my top module. Actually this is my top module. So in the top module, so this is basically my top module. Okay, so this is my top module. So this is my what? This is my full adder circuit. In the inside the full adder, you have two half adders, half adder 1 and next half adder 2, half adder 2 and one OR gate is there. Okay, so one half adder 1 and half adder 2 and one more OR gate is there. Okay, so how to write? So module full adder. So this is style 2. So port declaration, that is what are the inputs? These are the inputs, X, Y, Z, these are the inputs. What are the outputs? S comma C, these are the outputs. Okay, so I need to declare input X, Y, Z, output S comma C, and intermediate variables are there, no? S1 and C1 and C2. These are nothing but wire. These are nothing but wire. Wire I need to declare with wire. Wire S1, C1, C2. Okay. So normally you are not declaring any data type, means it will take as wire only. The default data type it is taking as wire only. Okay, if you want to declare as reg, means separately need to declare. Okay, so here input X comma Y comma Z means by default it is wire only, wire data type only. Okay, so next I need to instantiate two half adders and one OR gate. Okay, so how to instantiate means, see here, half. So what is my design name? This design name and this design name should be same, half adder, and my instance name. What is my instance name? HA1, HA1, and how you declared the inputs, that same way you need to declare here. Input A comma B, output sum comma carry, no? So here also, what are the input? X comma Y, and what is the output? S1 comma C1. Okay, and this is this half adder, this is HA1. Okay, so this is my HA1. Okay, similarly this is HA2. So HA2 also you need to instantiate. So half adder HA2, what are the inputs? S1 C1 and C2, S1 C1 and sum and C2. These are the outputs, these are the inputs and these are the outputs. Okay, and OR means gate level modeling in the OR R1. This is my R1. R1, what is the output? C, and inputs are C1 and C2.
So, or one here means
Hmm?
the last carry out. Or one.
Which one you are asking?
Last or one.
OR means gate level primitive. This is my OR gate, no? In gate level primitive, I told you, no? We need to use gate level primitive. We need to use
Yes,
gate
sir.
level.
Sir, after that
R1
or
is
one
nothing but
is
instance name. Instance name. This instance name. Gate level
okay.
instance name. R1. Or you can use A1 also. Nothing to worry. Just this is optional. Your
We
name.
can change it,
Yeah,
sir.
you can change A1 also.
Okay, sir.
Okay, A1. And what is the output? C comma C1 comma C2. C comma C is nothing but output. C is nothing but output, and C1 comma C2 end module. Okay, this is nothing but what? Connection by position with order list. Means how you declared in your design, that same order you need to follow. This is nothing but connection by position with order list. First is I told you, know, connection by position with order list. The second one I am doing connection by position with order list. Second one I am doing. Did you understood how I am instantiating? First I wrote the half adder code. So when it is instantiating, it will go to this code, okay, and it will execute this, okay. So it will execute. After that, again when I am instantiating, it will go to this code, it will execute, and next to OR gate. OR gate means this OR gate it will execute. So like this I can write the code for full adder by using two half adders and one OR gate. Did you understood how I am doing? Any doubts or queries? Waiting for your response so that I will move forward. Hello.
Yes, sir.
Okay.
Yes, sir. Got it.
Next you see. This is nothing but same thing. Full adder by using two half adders and one OR gate. Okay. Two half adders and one OR gate. One OR gate. Okay. So so first, so normally you wrote the half adder code. Okay. Here only you wrote the half adder code. This is my half adder code. Okay. After that, module full adder x comma y comma z. This is port rule declaration. Okay. Port list input x comma y comma z, output s comma y, and whatever the input internal variables are there, that you need to initialize with s1 c1 and c2. So this is nothing but connection by name. Connection by name, how it will be there means that is design name and followed by instance name, okay, followed by design input dot, you will get dot design input, and in bracket you will get top module input. Once design input and this module input you will get. See here. So if you see here, half adder, this is nothing but design name, and this is HA1 is nothing but instance name. This is my instance name HA1, and this is HA2. Okay, and this is R1. Okay, so half underscore adder. Okay, this design should be same. This design and this design should be same name. Okay, otherwise you will get compilation error. Okay, half adder HA1 dot and A is nothing but the outside the bracket is nothing but design inputs. What are the design inputs? A comma B comma sum comma carry, no. So these are the design inputs. A comma and x is nothing but my the top module input. Top module input is nothing but what? X is the input. Okay, comma dot b is my design input. This is design input, and y is my top module input. Okay, top module here y. Okay, inside whatever the top module is there, and sum is nothing but my design input dot sum comma s1. S1 is nothing but inside for this half adder S1. Okay, carry is my design dot carry comma this C1 comma C1. Okay, like this I need to write for HA1 half adder 1. Okay, similarly half adder 2 is there, half adder HA2 dot A is nothing but design input. This is design input comma what is the input for this half adder to S1, that will come in the bracket. Okay, comma dot b is my design input and what is the input you are getting Z for this half adder, comma, sum is my design input, comma, S is my output, okay, output, comma, dot carry, and C2 will get, and similarly this is by using gate level modeling I am writing OR, and gate level instance is R1, C comma, C2 comma, what is the one more input, this input C1 and C2, so this is nothing but connection by name. I am doing connection by name. So in industry they will use connection by name only, they will not use connection by position with order list, connection by name only they will use. Is it fine? Do you understood how I am doing? Understood?
Sir, first we need to assign the output values, sir.
What?
Sum and carry. And first we need to write sum and carry. Afterwards we need to write inputs. No, sir. For half adder 1 and half adder 2.
Half adder 1 and half adder 2 you are asking?
First we need to write outputs, no, sir.
No.
First we need to write sum.
No.
Sum
First,
and carry.
No. First we need to write, it means whatever may be the outputs or inputs, it will follow this one. That means the variables outside the bracket are nothing but design inputs and outputs. Variable inside the bracket are nothing but my module inputs, these module inputs. There is no like, actually normally you will get first inputs only you will get. First you need to declare the inputs only, after that you need to declare the outputs only.
For OR gate you have written first output, no, sir.
Actually this is nothing but gate level modeling. This is nothing but what? Gate level modeling. Gate level modeling, don't confuse with gate level modeling and instantiation. So gate level modeling means what? If it is gate level modeling, so this is a gate means, so I need to write, so what are the inputs for this gate? C1 and C2, and what is the output? C is there. So I need to write gate level primitive, the gate level primitive R, and gate level instance, that is R1. This is optional only, okay, it will be there or not, nothing to worry. Output C comma C1 comma C2, okay. Don't compare with the gate level modeling with instantiation. In the instantiation first you will get the inputs only. Here also, see here, first you need to declare. Suppose if you are declaring output first, means that order you need to follow. Here, connection by position with order list you need to follow. But here first inputs will come. Dot A means what? This design input. That means A. Okay. And dot B means this design input. And inside the bracket, this top module inputs you will get. X, Y. In test bench also will follow same thing only. Do you understood?
Okay, sir.
Yeah. Suppose I will show you one program related to this. One second. I'm opening. Verilog programs. Full adder using half adder. See here, full adder using half adder. I am opening the Xilinx Vivado. Just it will take time. Just wait. Yeah, opening. Yeah. This is a full adder using half adder. First I wrote for half adder. Actually, first I wrote the program for half adder. Okay. So here same thing. Module half adder input A comma B, output sum comma carry. I am using data flow modeling. That means assign sum equal to A XOR B, assign carry equal to A and B. Okay. By using data flow modeling I wrote. Okay. And after that, here I am writing for the full adder. Okay. So module full adder input A underscore FA, B underscore FA, output sum underscore FA, carry underscore FA. So internally I am declaring the wires W1, W2, W3, and this is nothing but connection by name. Connection by name with connection by name. This is a design name. What is my design name? Half underscore adder HA1 dot A. Dot A is nothing but my design input in the half adder. My design input dot A underscore FA is nothing but my top module. Okay, top module input. Dot B underscore FA, dot sum W1 dot carry W2. Okay. Similarly, half underscore adder HA2 also I am writing dot A W1 dot B in underscore FA, that is one more input, and dot sum underscore FA dot carry W3 I am getting. Okay. I am using assign statement. Assign carry equal to what? Carry underscore FA equal to W2 under or W3. Okay. So I told you, data flow modeling and behavioral modeling can be synthesizable. That's why I am using data flow modeling. Suppose if I want to see the code, elaborate the design. Just elaborate the design. I want to see the design. Okay. So that means the compiler will convert your code into the design. Okay. So this reading the netlist. It will take time. So for the simulation we need to write the test bench. Test bench not yet completed. That's why I'm showing the how to elaborate, how to see the code, how it is converting your code into the hardware. Okay. Yeah, see here, this is your design. Normally it is converted into half adder by using full adder by using two half adders and one OR gate. Two half adders. The compiler is converted this one into your program into this netlist hardware. Okay. Did you understood how I am getting the hardware in the Xilinx Vivado?
Yes, sir.
Okay. Yeah, vectors we'll see in the next class.